Okay, so that was without replacement on the deck of cards. This would be with replacement because on the coin, because each time I go to a new decision, the possibility is still there. Heads or tails, both are still available when I go here. Heads or tails, they're all still available when I go here. Choosing what to eat for Mr. Ho for 5 days in a week. That basically means Monday, Tuesday. I'm going to choose each different day. Monday, I don't know the lunch menu well enough to know how many decisions that there are. Let's say there are 50 different things you could choose to eat for lunch. I don't know, that could be wildly wrong. But the point is, really, I'm just trying to figure out if this is with or without replacement. I'm just trying to imagine here. So say there's 50 choices for the thing you want to eat on Monday. Could you possibly eat that same thing on Tuesday? In other words, are there still 50 choices here, or do we need to think about 49? Well, no. If you really like whatever it was you ate on Monday, it is possible, unlike decks of cards, it is possible to have the same thing each time. So you actually do have 50 choices. Now, if you had the same thing each time, that wouldn't. Um, if you knew you were going to have the same thing each time, there would be 50 choices for the first day, then there would only be one choice for the second day. But that's not what we're after here. We're after whether or not that's even in the pool of possibilities, because it adds to the total possibilities. It's not the only possibility, it's just one of 50, rather than taking out and having us have only 49. So this is also with replacement. It's a little bit harder to imagine because we don't know if it's exactly 50. And choosing to do that every day is not something everybody probably does. But maybe you do. I don't know. Lining up a class of kindergartners to go to PE class. Well, again, I don't know exactly how many kids there are. Let's say we have a class of, I don't know, 18 kids. So I'm not even going to draw 18 blanks, but how many choices do I have for the first kid? You can think that anybody in the class of 18 could actually go there. After that's assigned, how many do I have to pick from now for the second kid? Well, there's one kid already assigned. There's only 17 left to choose from. After two kids are assigned, there's only 16 left to choose from. In other words, after a kid gets assigned, he's taken out of the pool for being picked ever again. That's what happens when we put things in order. So this is without. This is a classic example of why you would want to use without replacement. I know the cards was kind of nice and kind of easy too, but this putting things in order thing seems to be really uh, popular too. That when you're putting things in order, like the books on the shelf I was talking about up here, putting things in order, then once you've used that outcome, once I've used Billy here for person number one, I'm never going to be able to use Billy again. And once I pick Jenny here for person two, I've got even fewer people I can now pick for number three, and so on. Okay, being assigned a 6-digit license plate for your car. What I meant by that was there's 6 spots on your license plate. And by saying 6 digits, I mean 6 numbers, kind of like a phone number where you have just the digits 0 through 9. A lot of states have way more complicated, and actually they make for some really nice probability um, questions. Uh, but for this one, let's just pretend that they're just the digits 0 through 9. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what I mean by digits. And we have 6 of them. So the first digit could be 0 or 1 or 2 or 3 all the way up to 9. The second one could be 0 or 1 or 2 all the way up to 9. How many choices are there for this whole thing? Well, I don't really need to know that right now. My question really right now is just, is this a with replacement or a without replacement kind of deal? Well, I have actually 10 choices for this first thing. 0, if you count 0 and you count all the way up to 9, if you count carefully, that's actually 10 different things it could be. After I choose the first digit, let's say that first digit is a 4. Could the second one also be 4? That's what this whole without replacement thing is. Could the second one be 4? Sure, it could. There's nothing wrong with having double 4s at the beginning of your license plate, or the same thing 3 times. In other words, it doesn't come out of the pool. Whatever choice I make, or whatever digit I'm given for the first digit, at least the way I'm defining my license plate here. Now, there may be some license plates in some states where they don't let you do that. That's really kind of crazy. I didn't talk about that here, but I guess I can imagine that that's possible. This gets really interesting when you start talking about states that have things like 3 letters followed by 3 numbers, and the number of choices is really crazy. Or they have 3 letters, and maybe the letters are without replacement, like you can't have any repeat letters, but you can have repeat digits, and then you got to be really careful. But this basic way I said it here with just 6-digit license plate, and any digits are possible anywhere. You could have all zeros. That's one of the possibilities. If you didn't let me have any of the same replacement, repeated digits, that makes a huge difference. Okay, you saw a little bit already about how the with or without replacement is going to make a big difference when I go to count things. If it's with replacement, like the multiple choice or the true false, I'm just multiplying up how many questions I have. Uh, that's how many times I'm going to multiply the number of choices. So it was like, 4 times 4 times 4 times 4. If I have multiple choice of 4 possible selections, like A, B, C, D, and there's 10 questions, this turned out to be 4 to the 10th power, because I have 4 choices for the first one, 4 choices for the second one, 4 choices for the third one, and that keeps going on. So the exponent is going to be how many choices you need to make, how many questions there are to answer, and n there is going to be how many choices you have each time. So when you're flipping a coin or doing true false, it'll be 2 to some power, however many times you're going to do it, because you have 2 choices, and then 2 choices, and then 2 choices. I think you can get that from there. So that's kind of easy to count. Without replacement isn't much harder. Without replacement just means, well, here, let's say we have 10 kindergartners to put in order. It's kind of like we just did a minute ago. I got 10 choices for the first person, but then for the second person now I've only got 9 that can go there after the first person gets assigned. And as I get down the list, you can imagine having these 10 kindergartners, you start to put them in like, say, 10 different seats. By the time you get down to the last seat, there's actually no decision to make. There's only one person left standing. You stick him in the seat and you're done. So it starts to look like this. You get these decreasing multipliers. You get slightly fewer choices each decision, because every time you make a new decision, you've assigned someone to one of these earlier things. You've taken them out of the pool. You've got less of a choice to make here. Whereas in this one with multiple choice, that decision number never goes down. It's a repeated of the same number multiplied over and over again. Here they're going to go down. This happens so much in math. We have a nice snazzy notation for it. It's this factorial. It doesn't mean I'm shouting at you. It means 10 times, 9 times, 8 times. It means exactly this. It means multiply all those down to till you get to 1. And it turns out for 10, that's a very big number. For just 10 people you're trying to put in order, there's over 3 million ways to do that. And that's actually true. Okay. So yeah, talk about this here. Oh yeah, and that is in your probability menu on your calculator. If you look here at, I'll do all these at once now actually. Oh no, I won't. I'll do them one at a time. In the probability menu, which we've been talking about a lot, and there's how you find it. It's math, and then you just go, you scroll this way, or you scroll actually left. You can come around and get the probability menu. The fourth thing down there is the exclamation point. I didn't put a number here ahead of time, but I could have. Let me get out of this. Let's say we want to find, I'll get rid of that. Actually, I'll get rid of that too. If I want to find 10 factorial, I go 10, math, left, 4. That will work. It gives me the factorial sign. Hit enter. It tells me what that is. That's where I got that number, by the way. 3,628,800. And that is really nice because it'll do that for you all at once. So what we just learned then is that whenever you're trying to make a lineup of n people, like say you had 10 people, and you want to put them all in order, you just have to take that number and factorial it. So that's why that thing is so popular, because it shows up as that a lot. In the book they say there are n factorial arrangements of a set that has exactly n elements. Now we're actually all ready to go straight into 7.4, which is really very closely related to that. It's just taking that idea of factorial and making it a little more, well, I say more general here. It's general because it includes factorial, but it's also like taking the factorial idea and tweaking it a little bit. It's about putting things in order, but sometimes you don't have to use the entire set of all the things you started with. Like if we had those 10 people and we want to just select 4 people in order, such as, person number 1, person number 2, person number 3, person number 4, or, these titles. How many ways are there to pick these 4 officers from a group of 10? Well, if you think about the decisions you have to make on that, I've got it right here, you have 10 choices for who could be president. President could be one of the 10 people. After you've done that, there's only 9 choices for the vice president, 8 choices for the secretary, and 7 choices for the treasurer. So it's like we started off at 10 factorial here, but we stopped because we weren't able to, we didn't need to make any decisions after this. We got through first, second, third, fourth place, and then we actually stopped because our job is done with a situation like this. This happens often enough that this is called permutation. Permutation, the way this is read is I'm taking a permutation of 10 things 4 at a time. Some people like to read this 10p4. I guess I don't have a problem with that, but your next teacher might laugh at you. You call that 10p4. It's a permutation of 10 things taken 4 at a time, and that's how they say it in the book. And yeah, it gets pretty big numbers pretty quickly too. I don't know if you sort of estimate that. Like you're going to pick 4 officers out of of a set of 10 people, there's over 5,000 ways to do that. Those numbers start out pretty small, but actually they end up quite large as a number of possibilities. That's why when we go to calculate probabilities, we got to be really careful because these numbers get out of hand really fast, especially if we do it wrong. Let me show you how to do this in the calculator. It looks like this in the calculator. It is the same menu that we've been used to, but you have to enter the 10 first, the number of sort of people in your list, the number of things you're going to pull from, and in the probability menu there's this NPR. It's the second thing there. 10 NPR 4. The calculator knows that that means start with 10 and start multiplying down. 10 times 9 times 8 times 7. Okay, I've counted 4 numbers. 10, 9, 8, 7. That's 4 numbers. Starting with 10, multiply them all, and you get this. Whereas when it sees this, it knows to go from 10 times 9 times 8 all the way to 1. This one says start at 10 and do that, but do the first 4 elements of it and stop and tell me what you got. How do we do that sort of technically? Like, what's the calculator really doing? Or if all it knew how to do was do factorial, how would it actually do that? Well, you think about this 10 times 9 times 8 times 7, how closely that is related to 10 factorial. It's like 10 factorial, but it stops at 7. In other words, it's like taking, let's see if I can do it this way. It's like taking 10 times 9 times 8 times 7, like all of it. Let's see if I have room to fit this in. It's like 10 times 9 times 8 times 7. Get my pen to work. 6, 5, 4, 3, oh, come on, 2, 1. But I really don't want all of that. I just want to stop at 7. So I need to get rid of all of these. Well, you can't just get rid of these. These mean something. You could divide. If I divided it by these, then yeah, that would cancel these out. So it's like I have to take 10 factorial and divide it by this little bit here that's going to have to cancel out what I have above. So this does equal what I'm talking about. I just have to think about taking 10 factorial. Did I write it for, yeah, it's right there. It's like I took the 10 factorial on top, and I wrote 6 factorial on the bottom. 6 factorial is this business right here. So if I took 10 factorial divided by 6 factorial, what I'm left with is the part of 10 factorial that sort of sticks up beyond 6 factorial. Because 10 factorial is all of this divided by the rest of this, and that will cancel itself out. So I should have wrote this backwards, but that's what it would look like. So that's how it's defined in the book. Where did the 6 come from with the original 10 and 4? Well, guess what? 10 minus 4 is 6. 10 minus 4 is all the rest of them that I'm going to be taking off. So if you look this up in a book, you might find this definition for what this notation means. I think this looks crazy. Like, who's going to remember all this crazy stuff with the subtraction before the factorial? I think it's easier to remember 10p4, 10 things taken 4 at a time, if you just think of it as, oh yeah, I'm going to start off 10 factorial, and I'm going to go 4 places and stop. So let me do another one. Let's say you had to do 7 things taken 3 at a time. Well, that means you'd start off with 7 factorial, and you're not going to go to 3. You're just going to do 3 numbers. 7 times 6 times 5. 5 is the third one in that list. It's like I need to make 3 decisions. It's like I'm answering 3 multiple choice questions. Oh, actually, I shouldn't say it that way. I need to pick a committee of 3 people from a group of 7. I have 7 choices for person 1. I have 6 choices for person 2, 5 choices for person 3, and I stop at person 3 because that was my original job. And I believe that's it for this lesson. Let me just make sure here at the end. I have a minute longer on this video. I could record. No, that's it. Oh, okay. There is one more little thing. What happens if we take 0 factorial? 0 factorial is defined to be 1. Why is that? Well, it's kind of as depressing as the answer to why is anything taken to the 0th power 1, like 5 to the 0th power. Why is that 1? Why is that the same as 100 to the 0th power? This is kind of the same thing. You start doing these calculations and subtracting before you do this. If n and r were equal, look, we'd have that situation right there. We don't want that to be an impossible fraction, so here's the sort of the short answer. Since that happens so often, mathematicians just define this, and the calculator knows this, and it makes everything play nice, and you don't get a domain error there. Okay, that's about it. I'll see you in class.